Hello learners, I am Dr. R.B. Malathi, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying Application and Techniques. In this module, our focus will be on the following key topics. First, we will have an understanding of the basics of tacheometry. Here, we will learn the definition and the instruments used in tacheometry surveying. A knowledge of how to hold the staff and determine the staff intercept will be given to you here. Next, we will have an overview of tacheometric measurements. Here, we will understand the systems of the tacheometry, that is a stadia hat system and the tangential system, and also learn the principles of tacheometry. Next, we will understand specifically the stadia hat method. Yes, here we will explore the distance and the elevation formula for horizontal sides of fixed hair method. Finally, we will practice some example problems. So, by the end of the lecture, I want you to have a comprehensive understanding of the stadia hat method for horizontal sides in surveying. Let us do a background study with chaining. Chaining, as you know, is a traditional technique that involves measuring horizontal distance using a chain or tape. It is a straightforward method and highly effective on flat, open ground. However, its accuracy decreases on rough or uneven terrain. This limitation can be significant drawbacks in areas with challenging landscapes. So, now to address this limitation, we often turn to tacheometry. Unlike chaining, tacheometry, which is also known as tachymetry or telemetry, is an optical method that measures both distance and angles. This makes it particularly suitable for rough terrain and quick observations. Now, let us closely see where tacheometry finds its application in the field of surveying. One of the primary uses of tacheometry is creating contoured plans. Why do we need contoured plans? Yes, these detailed topographic maps are essential for visualizing the terrain and understanding the lay of the land. Whether you are planning a construction project or studying the natural landscape, contoured plans are quite invaluable. Next, tacheometry is also suitable for preliminary surveys, particularly for large infrastructure projects like railways, roadways, canals and reservoirs. It allows surveyors to quickly access the terrain and gather necessary data, making it an efficient choice for early stage planning. Additionally, tacheometry can be employed in high accuracy surveys to check the distance measured by chain or tape. This ensures precision in the measurements and helps identify any discrepancies that might have occurred with traditional methods. Okay, having seen the application, now let us talk about the instruments used in the tacheometric survey. First, let us see tacheometry itself. Tacheometer is a transit theodolite equipped with stadia wires in addition to the usual cross wires. The stadia diaphragm consists of one stadia hair above and the other at equal distance below the horizontal crosshair, all in the same vertical plane as the horizontal and the vertical crosshair. So, when using a tacheometer, observations are made on a stadia rod, also known as level staff. This rod typically has a larger least count, usually around 1 centimeter, which gives a higher degree of accuracy. From these observations, both horizontal and vertical distance can be easily computed. So, vertical holding and normal holding of the stadia rod is important for achieving accurate measurements. So, let us discuss on it now. Vertical holding is generally easier as it ensures the staff remains perfectly upright, making it simpler for surveyors to maintain alignment. In ordinary work, the verticality of the staff can be judged by the eye, but in precise surveying, it is judged with the help of plumb bob. However, even minor deviations in verticality can lead to significant computational inaccuracies. Conversely, normal holding, which requires the staff to be perpendicular to the line of sight, not only avoid measurement errors but also maintains the integrity and reliability of the data collected. But this can be challenging, especially in high winds or rough terrain area. So, let us now look into the techniques used in practice for this proper holding. One common method to check the perpendicularity of the stadia rod involves a use of open sights. This technique entails sighting the instrument along the rod and ensuring it is aligned correctly. The observer uses the open sights to verify that the rod is perfectly upright and perpendicular to the line of sight. This simple yet effective method is favored in the field due to its ease of use, reliability and the minimal equipment required. Another method for ensuring the perpendicularity of the stadia rod is by using a small telescope fixed at right angles to the side of the rod. The staff is inclined until the telescope of the tacheometer bisects the cross wires of the telescope fixed to the rod. This alignment process is important because it directly affects the accuracy of the distance measurements. Now, to identify the staff intercept, the procedure is: the telescope is directed to the side of the staff. The telescope is then adjusted by means of the vertical tangent screw until one stadia wire aligns with the graduation on the staff. Then the other stadia wire is read. The difference between these readings gives the staff intercept. Subsequently, the middle cross wire and the corresponding vertical angle are also recorded. Some surveyors adjust the middle hair reading to match the height of the instrument to simplify the calculations. However, this practice should be avoided as it introduces errors due to the refraction of rays close to the ground, leading to inaccurate observations. Now, having understood the various holdings and understanding the procedure for determining the staff intercept, let us move to the third instrument, that is the substance bar. The substance bar, also known as horizontal stave, is an important instrument used in surveying for measuring both horizontal and vertical distance. It is particularly useful in areas where traditional chaining methods are impractical due to uneven or rough terrain. The substance bar is most effective for determining short distances, typically up to 200 meters. Its unique design allows surveyor to accurately measure distance in challenging environments. And figure of the substance bar here shows its configuration and components. And the substance bar shown here consists of a horizontal metal bar with two targets fixed at a known distance ranging from 0.3 to 3 meter apart. In India, these bars are usually about 3.5 meter long. Mounted on a tripod, the bar is levelled using a small spirit level, then clamped securely in place. The targets, generally 20 cm in diameter and painted in contrasting colors, assist in measurement accuracy. Some targets are square as shown in the diagram. Yes, now how do you compute the horizontal and vertical distance accurately? For that, you align and level the bar and clamp it in place. The theodolite reads the horizontal angle between the targets and the vertical angles to the bar, and from these readings compute the horizontal and the vertical distance accurately. Okay, now let us see how tacheometric surveying is carried out using different systems. The primary systems include the stadia hat system and the tangential system. The stadia hat system is particularly significant and can be divided into two specific methods, that is the fixed hat method and the mobile hat method. And each of these methods has distinct characteristics and applications, offering different approaches to measure distance. So, let us first look at the fixed hat method. The fixed hat method within the stadia hat system involves setting the stadia hats at fixed intervals. The intercept on the leveling staff or stadia rod varies based on the horizontal distance between the instrument station and the staff. The intercept is calculated by subtracting the lower stadia reading from the upper stadia reading. In cases where the staff intercept exceeds the staff length, only half of the intercept is read. This is determined by the difference between the central stadia hat reading and either the lower or upper stadia hat reading, ensuring accurate measurement even with the larger intercepts. This fixed hat method can be used effectively even when horizontal sights are not possible. For inclined sights, accurate readings can be obtained by holding the staff either vertically or perpendicular to the line of sight. This method is considered the most common form of tacheometry and is frequently referred to as stadia hat method. And its adaptability and accuracy make it a preferred choice for various serving scenarios. In contrast, the mobile hat method keeps the intercept on the leveling staff constant while considering the distance between the stadia heads to vary. This method involves fixing two targets on the staff at a known distance apart and adjusting the stadia hat so that the upper hat bisects the upper target and the lower hat bisects the lower target. This adjustment allows for the measurement of variable intervals between the stadia hats. Similar to the fixed hat method, readings can be taken with the staff held either vertically or perpendicular to the line of sight, accommodating different sighting conditions. The tangential method, unlike the stadia hat methods, does not use stadia hats. Instead, readings are taken on a staff against the horizontal crosswire of the instrument. To measure the staff intercept using this method, two pointings of the telescopes are required. Typically, staff readings are taken at full meter value to avoid dealing with decimal parts, which simplifies the computations. Although this method is effective, it is less commonly used due to the necessity of measuring two vertical angles for each observation, which can be more time consuming and complex compared to the other methods. In conclusion, both the stadia hat system and the tangential method offer distinct approaches to tacheometric measurement. The stadia hat system, including both the fixed and mobile hat method, is valued for its precision, making it a popular choice. On the other hand, the tangential method, which is less common, provides an alternative approach where stadia hat methods are not used. And understanding the strength and application of each method helps in selecting the most appropriate technique for specific surveying needs. So, let us now look into the principles of tacheometry. The principle of tacheometry is grounded in a key geometric relationship involving isosceles triangles. The principle asserts that in isosceles triangles, the ratio of the perpendiculars drawn from the vertex to their bases remains constant. To understand this, consider two isosceles triangles ABC and ABC' as shown in the figure. In these triangles, the bases are BC and B'C' with the vertex positioned at A. The perpendiculars from the vertex A to the bases labelled AO and AO' respectively represent the height of the triangles. The ratio of AO to AO' remains constant due to the isosceles nature of the triangles. Now for horizontal sides, the similar triangle principle can be used to calculate the difference in elevation between the instrument station and the staff station, like the differential leveling. So, the relevant formula is AO by BC is equal to AO dash by B dash C dash is equal to 2 cot alpha by 2, which is equal to K. This can be easily understood from the figure. So, kindly see the figure closely. BC is equal to BO plus OC, that is tan alpha by 2 plus tan alpha by 2 is equal to 2 tan alpha by 2. Therefore, AO is equal to BC into 2 cot alpha by 2, where alpha represents the apex angle of the isosceles triangle and K is a constant dependent on the alpha. Repeat, where alpha represents the apex angle of the isosceles triangle and K is a constant dependent on alpha. Let us now determine the distance and elevation formula for fixed air method of stadia air method. As depicted in figure, the setup involves a tacheometer, telescope and a stadia rod. Through the telescope, the surveyor views the stadia heads intersecting the rod at the points A and B. The rays from the stadia heads A dash and B dash passed over the optical center of the objective lens and continue to intersect the rod at B and A. This setup is essential for understanding how distance and elevations are calculated using the stadia head method. In this method, several parameters are important, so let us see one by one. O represents the optical center of the object glass, A dash and B dash are the stadia wires and the distance A dash B dash is the stadia interval. The horizontal cross wire position is denoted as C dash and AB represents the staff intercept labeled as S. The focal length of the object glass is F, with F1 and F2 being the conjugate focal lengths of the lens. The distance between the vertical axis of the tacheometer and the optical center is D, and capital D is the distance between the tacheometer and the staff, and I is the stadia interval. So, from the similar triangles AOB and A dash OB dash, AB by A dash B dash is equal to OC by OC dash is equal to F1 by F2, or simply we can write as S by I is equal to F1 by F2. And we know the lens formula, that is 1 by F is equal to 1 by F1 plus 1 by F2. This can be written as 1 by F is equal to F2 plus F1 by F1 F2. Now, by taking 1 by F1 out, it can be rewritten as 1 by F1 into F2 plus F1 by F2. So, 1 by F is equal to 1 by F1 into F2 by F2 plus F1 by F2. Here F2 and F2 get cancelled and we get F1 by F is equal to 1 plus F1 by F2. Hence, substituting for S by I is equal to F1 by F2 leads to F1 by F is equal to 1 plus S by I. Taking S by I to the left side, we get S by I is equal to F1 by F minus 1. This can be further written as S by I is equal to F1 minus F by F. Now, taking F to the left side again, S by I into F is equal to F1 minus F. Again, taking F to left, we get S by I into F plus F is equal to F1. Now, adding D on both the sides, we get F into S by I plus F plus D is equal to F1 plus D. We know F1 plus small d is equal to capital D. Hence, rearranging the equation, we get capital D is equal to F by I into S plus small f plus D, or capital D is equal to Ks plus C. This equation is known as the tacheometric distance equation. Here f by I represented by capital K is called the multiplying constant and f plus d represented by capital C is called the additive constant. The multiplying constant capital K is also known as stadia interval factor and it is important for accurate distance computation. Typically, K is kept as 100 for easier computation. In practice, if an analytic lens is used, that is a special convex lens fitted in between the object glass and the eyepiece is used, its function will be to reduce the stadia constant to 0. That is, it ensures that all observations are reduced to the center of the instrument, making K is equal to 100 and the constant C is equal to 0. As a result, the equations becomes D is equal to 100S, allowing for the straightforward distance measurements. Typically, the value of C ranges from 0.25 to 0.35 here. But in practical scenarios, the line of sight is rarely horizontal due to the ground undulations or difference in elevation between the staff and the instrument station. When this occurs, the staff should be held vertically or perpendicular to the inclined line of sight. To determine the constant K and C experimentally, a line approximately 200 to 250 meter long is set out with pegs at 25 to 30 meter intervals. Staff intercepts are obtained at these pegs and several equations are formed like D1 is equal to Ks1 plus C, D2 is equal to Ks2 plus C and D3 is equal to Ksc plus 3. And solving these equations in pairs yields several sets of constants K and C. The mean values of these constants are then reported for accurate tacheometric measurements. Now, let us look into some example problems. So, the first example here is, following are the data of an externally focusing telescope used for a tacheometric survey. Find out value of the multiplying constant and the additive constant. So, the staff intercept is 1.52 meter, interval between stadia here is 5 millimeter, distance between the vertical axis of the telescope and the object is 120 millimeter, focal length of the object is 0.3 meter. So, what are the given data? S is 1.52 meter, I is 5 millimeter, F is 0.3 meter, that is 300 mm, and small d is 0.12 meter. And we are asked to determine the multiplying constant and the additive constant. So, let us work out the solution. We know the multiplying constant K is equal to F by I. So, substituting the values, K is equal to 300 by 5, which is 60. Next, we are supposed to determine the additive constant C. C is equal to F plus D, which gives 0.30 plus 0.12, which is 0.42 meter. The summary here is the multiplying constant is 60 and the additive constant is 0.42 meter. Next example, a tacheometer has a diaphragm with 3 crosshairs spaced at the distance 1.15 mm. The focal length of the object glass is 23 meter and the distance from the object glass to the trunnion axis is 15 centimeter. Calculate the tacheometry constants. Here is a figure for you to visualize the problem. Hope you could clearly see the 3 crosshairs spaced at the distance 1.15 mm here. So, let us start solving the problem. Let us write down the given data. The focal length of the object glass F is 23 centimeter, which is 0.23 meter. The distance from the object glass to the trunnion axis small d is 15 centimeter, that is 0.15 meter. Now, I is equal to 2 into 1.15. Why 2 into 1.15? Because the distance between the crosshair is 1.15 and the stadia interval is a distance between the outer stadia wire. So, it will be 2 times the distance between the crossfire, that is why it is I is equal to 2 into 1.15, which is 2.30 millimeter or 0.23 centimeter. Now, we need to determine the multiplying constant and the additive constant. The solution is the multiplying constant K is equal to F by I, which is 23 by 0.23 gives 100. And the additive constant denoted by C is equal to F plus D. Substituting the values of F and D, we get 0.23 plus 0.15, which is 0.38 meter. The summary is the multiplying constant is 100 and the additive constant is 0.38 meter. Moving to the next example. The stadia hair readings with the horizontal side on a vertical staff held 50 meter from a tacheometer were 1.685 meter and 2.320 meter. The focal length of the object glass was 25 centimeter. The horizontal side on a vertical staff was 15 centimeter. Calculate the stadia interval. A figure is given here for you to visualize the stadia hair readings from the tacheometer, that is 1.685 meter and the 2.320 meter. Hope you can easily visualize it. Now, let us see the solution. Writing down the given data, the horizontal side on the vertical staff capital D is 50 meter, the lower staff reading small s1 is 1.685 meter and the upper staff reading s2 is 2.320 meter. The focal length of the object glass small f is 25 centimeter, which is 0.25 meter, and the horizontal side on the vertical staff small d is 15 centimeter, which is 0.15 meter. We are supposed to determine the stadia interval I. The solution is I can be determined from the formula D is equal to F by I S plus F plus D, which you know. Here we need to determine S. What is S? S is the upper staff reading minus the lower staff reading. That is S is equal to S2 minus S1, which is 2.320 minus 1.685, which gives the value 0.635 meter. Now, substituting this value in the capital D, 50 is equal to 0.25 by I into 0.635 plus 0.25 plus 0.15. Solving, we get I is equal to 3.2 into 10 power minus 3 meter, which is 3.2 mm. Summary here is the stadia interval I is 3.2 mm. Moving to the next example, the stadia reading with the horizontal side at a vertical staff held 50 meter away from the tacheometer were 1.225 and 2.390 meter. The focal length of the object glass was 25 centimeter. The distance between the object glass and the trunnion axis of the tacheometer was 15 centimeter. Calculate the stadia interval. A figure is given here for you to clearly visualize the problem. So, seeing the figure, write down the given data. The data are S1 is equal to 1.225 meter, S2 is equal to 2.390 meter, F is 25 centimeter, which is 0.25 meter, small d is 15 centimeter, which is 0.15 meter. You are supposed to determine the stadia interval I. So, the solution is I can be determined from the formula capital D is equal to F by I into S plus F plus D. S is equal to S2 minus S1, which is 2.390 minus 1.225, which is 1.165 meter. So, substituting the value of D in the equation, we get 50 is equal to 0.25 by I into 1.165 plus 0.25 plus 0.15. From this, we can determine I as 5.9 into 10 power minus 3 meter, which is 5.9 mm. So, the summary is the stadia interval is 5.9 mm. Let us move to the next example. Calculate the value of K and C if the measurements are taken between 2 points of 150 and 130 meter distance apart and the stadia intercept readings are 0.024 and 0.824 meter respectively. See the figure and read the problem again for easy understanding. So, what are we supposed to do? We need to calculate the values of K and C if the measurements are taken between 2 points 50 and 130 meter apart with the stadia intercept reading I is 0.024 and 0.824 respectively. So, let us work out the problem. The given data here is capital D1 is 50 meter, capital D2 is 130 meter, S1 is 0.024 meter, S2 is 0.824 meter. And we are supposed to determine the tacheometric constants K and C. The solution is use the tacheometric formula D is equal to Ks plus C. So, for 50 meter D1 is equal to Ks1 plus C. So, 50 is equal to K into 0.024 plus C, that is the equation 1. And for 130 meter D2 is equal to Ks2 plus C, that is 130 is equal to K into 0.824 plus C, that is equation 2. So, equation 2 minus equation 1 will give 130 minus 50 is equal to K into 0.824 minus 0.024, that is 80 is equal to 0.8 K. Solving, we get K is equal to 100. So, putting the value of K in the equation 1, 50 is equal to 100 into 0.024 plus C. So, 50 is equal to 2.4 plus C. From this, C is equal to 50 minus 2.4, which is 47.6 meter. So, summary is the tacheometric constant K is 100 and C is 47.6 meter. I hope this class provided a solid foundation for understanding the principles and applications of stadia head method in tacheometry. Let us learn more about tacheometry in the upcoming classes. Thank you and happy learning.